Today we are going to cover processor logic design. The topic we are going to cover at the beginning is the processor organization. A processor unit is a part of a digital system that implements operations in the system. It comprises a number of registers and digital functions that implement arithmetic, logic, shift, and register micro operation. The processor unit, when combined with a control unit that supervises the sequence of micro operations, is called a central processing unit. In short, we call CPU. A central processing unit CPU consists of memory, we call register banks, arithmetic logic unit ALU, and the control unit CU. So again, a central processing unit CPU consists of memory, sometimes called register banks, arithmetic logic unit, the ALU, and the control unit CU. There are three organizations for organizing a general purpose processing unit. Now, inside the CPU, how different components get connected, how they operate. There are three organizations. The first one is called bus organization. Second one, SCRATCHPAD memory. Third one, this is the two-port memory. On the next slide, we'll investigate the bus organization. Look at the picture, okay? This is called bus organization. Why bus organization? If you look at the picture, different components. This is the registers, this is the arithmetic logic unit, okay? And control units and different control signal. Control unit has not been shown over here, but the signals, look at over here, A select. This is the control signal. B select, function select, shift select, destination select. They are the control signal. A bus organization has 4 registers. This is a model example. In this case, it has 4 registers. Register R0, R1, R2, R3. 4 registers, okay? Each register is connected to 2 multiplexers to form 2 buses A and B. Look at over here. All the registers, each one is connected to multiplexer. Multiplexer A and multiplexer B. Multiplexer has 4 input and 1 output. This is the A bus and this is the B bus. Okay, so this is the A bus and this is the B bus. To perform the microoperation, so we'll take one sample microoperation. We'll do addition of register R2 plus R3, and the result will be stored in register R1. Okay, so this is a sample operation that we are going to implement with this bus organization. So how this will get performed? Look at over here. First thing, we need to read register R2 and register R3 through the multiplexer. So to select register R2 and R3, we need to give control signal to the multiplexer. Let's say A select. There are 4 registers. So we need 2 selection pin to select 1 out of 4 registers, right? 2 to the 2 equal to 4. So we need 2 selection pins. So there will be 2 selection pins to select 1 out of 4 registers. So we select register R2 by multiplexer A and it comes to the A bus. Again, by using the selection pin that is generated by the control signal, we select register R3 and it comes through the B bus system to the ALU. So A bus holds the data A that comes from register R2, B bus holds the data B that comes from register R3. So this is the 2 data item that is input to the arithmetic logic unit. Okay. Next, what we need? we need the control signal from control unit to perform the addition operation. After addition operation, we use the shifter to shift the output or to shift the result to the output bus, S bus. Again, different way, the result from the ALU can be shifted. In this case, we'll use the operation called no shift. That means there's no left shift or no right shift. Just direct result will come to the S bus output bus. This is called no shift, okay, operation. So shifter has many functionality. We'll see the other slide how shifter is designed and how it performs different type of activity or shift operation. But in this case, it is no shift. That means directly the result will come to the output bus or S bus. Then it need to be saved to the destination. This output bus is connected to all the register. Okay, data is available or result is available at the input of all the register. But we need to save the result only in the register R1. So how to do it? By this decoder. Destination select is a signal from the control unit. Okay, this destination select will select the particular register. Okay, then data will get written in that register R1. So what happens? Let's see one by one. Multiplier A selector to place contents of R2 onto bus A. Then multiplier B selector to place contents of R3 into bus B. ALU function selector to provide the arithmetic operation A plus B. Shift selector for direct transfer from the output of the ALU onto the output bus S. Is the no shifting. Finally, decoder destination selector. Decoder destination selector to transfer the contents of bus S into the register R1. Now, how many operations? 1, 2, 3, 4, 5 operations. All 5 operations will be performed in a single clock cycle. And what control unit will do? Control unit generate all the control signal. Signal A, signal B, function select, shift select, destination select in a single clock cycle. In a single clock cycle, all the signals will get generated, and the entire R plus 2 addition operation and the saving the result into the register R1 will be performed in a single clock cycle. Okay, so control unit generate all the signal together, and we sometimes call this the control word. This control word will perform the entire addition operation and the saving the result in the register R1 in a single clock cycle. So what we see? Operation is faster. Only a single clock cycle is required, but cost is little bit higher because lots of wire connection, lots of different components. Okay, lots of connectivity. Complexity little bit higher, but faster operation. So this is the bus organization. Okay. Now second one is the SCRATCHPAD memory. What is SCRATCHPAD memory? Look at over here. This is the SCRATCHPAD memory. In the SCRATCHPAD memory, what we do? In this case, we don't use separate register like R0, R1, R2, R3, R4 like that. No separate register. We use a single pitch of memory, and each cell of the memory is treated as a register. For example, this will be treated as a register. First cell, register R0, the register R1, register R2, R3, R4, R5, so on like that. Depending on the size of memory, it will contain a set of registers. Each cell will be treated as a register. That's the SCRATCHPAD memory. We don't use separate memory cell. A single memory, each cell will be treated as a register. So what we see over here? Simplicity. Low cost. Because we don't need to connect separate registers separately with the buses. Okay. So in SCRATCHPAD memory, we use a single picture memory, and each cell of the memory is treated as a register. Okay. So how it works? This is the multiplexer. This is the input data. Okay. By using the multiplexer, data can come from two different sources. This is two input and one output of the multiplexer. One is the input data, other is the output from the shifter. Okay. Now let's do the same operation like before, R2 plus R3, and the result will be stored in register R1. Let's see how it works over here. To perform the operation R2 plus R3 and the result get stored in register R1, the control must provide binary selection variable to perform the following sequence of 3 micro operations. Look at over here. In clock cycle T1, we need to read word A from the memory. This is R2. Capital M stands for memory. Capital M stands for memory, and this is the address, location 2, like register R2. So we read R2 from memory. This is R0, this is R0, R1, R2. Okay, this is register A.
As usual, group 1.
So in the first clock cycle, we read register location R2 to register A. On the second clock cycle, we register R3. Okay, from the memory into the register B over here. Register B. This is register B. This is register A. Okay. So 2 clock cycle is required to read word A and word B. Okay. After reading word A and word B, we perform arithmetic logic operation, addition operation. Okay, in clock cycle T3. And after the operation, result will get stored through this multiplexer to the location R1. Okay, so look at R1. So what we see, there are 3 clock cycles required to perform this addition operation. Instead of 1 clock cycle that is required in the bus organization. So it is slower, even though the complexity is got reduced in the bus organization. Cost also is lower than the bus organization, but it takes more time, because instead of 1 cycle that is required in bus organization, it's taking 3 clock cycle. So this is the SCRATCHPAD memory. Okay, this is SCRATCHPAD memory holds different registers. Each cell is treated as a register. Now we can improve the performance of this SCRATCHPAD memory by another technique. Look at over here. This memory, we cannot read more than 1 data at a time. Single port memory. Look at over here. A single address. So what we can do, what improvement we can do? This is a single port memory. Look at over here. A single address is applied, then you read data. Word A, then word B. So we need 2 clock cycle to read 2 data at a time. Okay, 1 by 1 we need to read. We cannot read together. That's the drawback of the SCRATCHPAD memory. But there is technique that you can read more than 1 data item at a time in a single clock cycle. So this is a single port memory, and we need 2 clock cycle T1 and T2 to read word A and B. But there is memory available that is called 2 port memory. In 2 port memory, what we can do, look at over here. This is the 2 port memory. Look at over here. Some processors employ a 2 port memory in order to overcome the delay caused when reading 2 sources registers. If the destination register is the same as the one of the source register, then the entire microoperation can be done within a 1 clock pulse period. Look at over here. In this case, it has two ports, A address and B address. We can read two data items simultaneously. In that case, as in before, T1 and T2 is required to read A and B, but in two-port memory, only 1 clock cycle will be required to read A and B. So in that way, we can reduce 1 more clock cycle. Only 2 clock cycle will be required for there. Okay, so it can improve the performance to some extent at the expense of a little bit more cost for two-port memory. Okay, this is the two-port memory, A address and B address. Okay, so this two-port memory can improve the performance than the SCRATCHPAD memory. Okay, so three organizations we have seen: bus organization, SCRATCHPAD memory, and the two-port memory. Okay, next, what is next? The design of the arithmetic logic unit. If you look at over here on the right side, this is the arithmetic logic unit, ALU. Our job now, we are going to investigate how we can design the ALU. Okay, if you look at the ALU, it has two word input, word A, 4-bit. This is the word A. This is the word B. Both are 4-bit. The output is 4-bit. F is the output, that is 4-bit. Okay. This block has again 4 input on the right side. The input S2 is called mode select. Look at over here, arithmetic and logic operation. Two type of operation it will perform. When this mode select pin S2 is 0, then this block will perform arithmetic operation. When S2 is 0, mode select pin, it will perform only arithmetic operation. When the mode select pin, this S2 is 1, it will perform logic operation. What are the arithmetic operations? Addition, subtraction, multiplication, division, then A plus B, A minus B, A plus 2, A plus 5, all are arithmetic operations. Okay. What is the logic operation? AND operation, OR operation, NOT operation, explicit OR operation, shift operation. No, shift operation is not performed over here. Okay. For shift operation, we use shifter. Only logic operation get performed. Okay. Different type of arithmetic and logic operation get performed. For shift operation, we use another device called shifter. So mode select pin will decide whether your block or device will perform arithmetic or logic operation. If it is 0, arithmetic operation. If S2 is 1, it is logic operation get performed. Now there are two selection pins. Selection pin S0 and S1. Function select. They are function select pin. Okay. S0, S1, they are function select pin. S0, S1. By two function select pin, how many operations you can perform? 0, 0 for one operation, 0, 1 for another operation, 1, 0 for another, 1, 1 for another operation. So 4 different operations you can perform by two selection pin S0 and S1. Okay. And the fourth one is the carry in. Okay. Carry in. Carry in has significance for arithmetic operation because when you do addition or subtraction, carry or borrow signal get generated, right? But carry does not have any meaning in logic operation. In logic operation, it does not have any meaning, right? So if we include carry in as the third selection pin for arithmetic operation, S0, S1 and carry in. So there will be 3 selection pin for arithmetic operation and 2 selection pin for the logic operation, S0 and S1 only. So if there are 3 selection pin for arithmetic operation, then how many different operations can be performed by this ALU? 2 to the power 3. That means 8 different arithmetic operation can be performed. Okay, and 4 different logic operations can be performed in this case. So all the things are written over here. The mode select is to distinguish between the arithmetic and logic operation. I am starting from here. Okay. The two function select input S1 and S0 can specify the particular arithmetic and logic operation to be generated. The input and output carry have meaning only during the arithmetic process. The input carry seen is the least significant position of the ALU is quite often used as the fourth selection variable that can double the number of arithmetic operations. Thus, a total of 8 arithmetic operations and 4 logic operations can be performed. Okay. The basic component of the arithmetic section of the ALU is the parallel adder. So when we design the ALU, we don't use different hardware for different operations. It will only increase the complexity and cost. Instead, we play a trick. Okay, a trick or clever idea. What is the clever idea? Instead of using different hardware for different operations, we use a single hardware called parallel adder. This is a 4-bit ALU, so there will be 4 1-bit full adder cascaded together as parallel adder. So what is parallel adder? Do you know? Anyone has idea? What's parallel adder? Let me show you the picture of parallel adder. So this is our hardware. Look at over here. This is our hardware. There are 4-bit. Each bit we have a full adder. They're connected together as parallel. This is bit position A1, A2 or A0, B0, second bit, third bit, and fourth bit. This is the output. This is the carry in. Carry out of first 1-bit full adder becomes the carry in of the second full adder. Okay. So this is called parallel adder. 4-bit. So this is our basic hardware. Only a single hardware. By using this single hardware, we design the ALU. Okay, so this is our hardware. This is our hardware. What is the equation of sum of this hardware? Full adder. It becomes A exclusive or B exclusive or C. Okay. The equation of sum becomes A exclusive or B exclusive or C. So that's our basic hardware. 4-bit parallel. Okay. Now let's go back to our slide. So now we know the hardware. We are using a single hardware to do our design. A parallel ladder is constructed with a number of ladder circuits cascaded. By controlling the data inputs to the parallel ladder, it is possible to obtain different types of arithmetic operations. When the selection pin is S0, S1, they are 0, 1. Selection pin S0, S1, they are 0, 1. Then operation A and B get performed. Okay. In the design of the arithmetic unit, what we do, we only do the variation in B input, B1. We don't change the A1. So in the first case, when S0, S1, they are 0, 1, we don't change the input A and B. We keep as it is. Look at over here. When the carry in equal to 0, the result of addition becomes A plus B equal A plus B. Okay, simple addition. And when carry in equal to 1, it becomes A plus B plus 1. Addition with carry. Okay. So when the selection between S0, S1 they are 1, 0 or 0, 1, we get these two type of operation depending on the carry input. When the carry in equal to 0, we get simple addition operation. When carry in equal to 1, we get addition with carry. When the selection pin, look at over here. When the selection pin S0, S1, they are 0, 1. This combination, we get second set of defined two operation. In the second set, what we do? We modify the input B to B bar. This is B bar. This is bar over here. Okay. We invert the input B. By inverting input B, what we get? When carry in equal to 0, we get A plus B bar. That means A plus 1's complement of B. Okay. And when the carry in equal to 1, we get A plus B bar plus 1. That means we get A minus B. A minus B. B bar plus 1. If you take 2's complement of a number, it becomes a negative number. B bar plus 1 is equal to minus B. So what we get? We get subtraction operation in this case. A minus B. Okay. For the third selection pin combination, when S0, S1 they are 0, 0, again another two different operation we get. In this case, we modify B as 0. Instead of applying B, we apply 0. So we change B to 0 in the third combination. If we change B to 0, look at over here. When the carry in equal to 0, we get transfer of A, F equal to A. Okay, we get transfer of A. And when carry in equal to 1, we get increment of A plus 1. Okay, in the third case, we get transfer of A when carry in equal to 0, and when carry in equal to 1, we get increment of A. Increment of A. Okay, A plus 1. For the fourth case, when S0, S1, look at over here, they are 1, 1. Okay, this is the fourth case, last one. And in the fourth case, what we do? We modify B. Instead of applying B, we apply all 1. Okay, instead of applying B, we apply all 1 in the place of B. In that case, what happens? You can use your calculator, and if you add A plus all 1, your result will be A minus 1. So it is the decrement A operation when carry equal to 0. And when carry in equal to 1, this minus 1 plus 1 get cancelled, it becomes transfer of A. So what we see? For different selection combination, we get different output. Okay, depending on the first selection combination, at that time we don't change A and B. Okay, and we get two different operations. For the second selection combination, we modify B to B bar. Only we change B in this case. We modify B to B bar, and we get A plus 1's complement and A minus B operation. The third case, we modify B to 0, and again another two different operation we get. Okay, transfer of A and increment of A. The fourth case, again we modify B to all 1, and we get again two different operations: decrement of A and transfer of A. So what we see over here? By modifying input B, depending on the selection pin, we get different output or different arithmetic function. Okay, by modifying B, depending on the selection input S0, S1, and carry in, we are getting different arithmetic operation. So what is the next step? Because I have told you that we are not use different hardware, only single hardware, 4-bit per adder. So we need to design a circuit now. What our circuit will do? Depending on the selection input S0, S1, and carry in, the circuit will automatically modify this B. Because when you design, we don't need to manually modify B by ourselves each time, depending on the selection pin. We will design a circuit. That circuit will modify B depending on the selection pin S0, S1, and carry.
So in this rough way, so modifying B.
Yes.
Modify B and modify A.
Okay, we'll modify A during the logic operation. Because we are doing some clever design, only single set of hardware, 4-bit per adder. So to design the arithmetic circuit, we'll just modify B, and we will design the circuit for it. Automatically, it will modify B depending on the selection pin. And for logic operation, again, we will use A. We'll use modify A to get different logic operation depending on the selection pin. So in both cases, we need to design that circuit that will modify B automatically depending on the selection pin. Depending on the selection pin, it will modify B automatically. That's our next step. Okay, so let's see how to design the circuit. Okay, to modify B depending on the selection pin. So this is the summary of our entire operation of the arithmetic unit only. In this case, look at over here. This is the selection pin. Function select. Carry in S0, S1. Okay. Carry in S0, S1. So it can be 0, 0, 0, 0, 0, 1, 0, 1, 0. So we summarize. Okay. When it's all 0, transfer of A. 0, 0, 1, increment of A. You just summarize the operation in the tabular form over here. 0, 1, 0, A plus B. 0, 1, 1, A plus B plus 1. 1, 0, 0, A plus B bar. Okay, and so on. Now, to get this type of operation, these are the different operation, arithmetic operation. We have modified B. So we give a new name to this modified B called Y. Y is the name modified B. Y equal to modified B depending on the selection pin. Okay, Y is the modified B depending on the selection pin. When the selection pin is 0, 0, 0, we will modify B to 0. That is Y. Okay, when the selection pin is 0, 0, 1, it is B will be 0. That's come from the previous table over here. 0, 0, 1. Okay. So this comes from this table. When it is 0, 1, 0, y equal to b. So this y is the modified b. This y is the modified b. So we need to design the circuit that will do this modification automatically depending on the selection pin. Okay, so let's design the circuit. This is our truth table. When S0 and S1 they are 0, 0, look at over here. S0, S1 there when they are 0, 0. Y equal to 0. Okay, carry in just vary 0 and 1. So we just need to consider both these two because carry in get varied. Okay, it does not matter what is carry in, all the time it is 0, 0. Okay, when this selection input S0, S1 they are 0, 1 or 1, 0, if you read from right to left 1, 0, then y equal to b. It does not matter what is carrying. So when they are 1, 1, no, 1, 0, okay, or 0, 1, then it is b bar, y equal to b bar. When this selection is 0, S1 they are 1, 1, y equal to all 1, that is b equal to all 1. So we summarize this fact in a tabular form over here. Clear? We summarize this fact in a tabular form over here. So this is the truth table. So now we can easily find the equation of y. What is the equation of y? Get the equation of y from here. This is the equation of y. B S0 and B bar S1. Look at over here. This is B S0, B bar S1. This is the equation of y. B S0, B bar S1. This is the equation of y. And we don't modify A, so we use two new variables, x and y. X is the modification of A. In this case, we did not do it. We will do modified of A in the logic design. In the arithmetic design, we have just modified B. So y equal to modification of B. And this is the circuit for it. This circuit will do the modification automatically. Okay. So x equal to A and y equal to B S0, B bar S1. So now design the circuit. This is your circuit. This is your circuit. Okay. B S0. This is B. This is S0. Okay. And this is B bar S1. So this is the our logic circuit for the output or for the input y. Y is the modification of B. And for x equal to A, there's no change over there. So we introduce two variables x and y. X is the modification of A and y is the modification of B. In the arithmetic design, we only modify B. So this is the logic equation of y. Okay. And look at over here. Now this is our complete circuit. This is 4-bit parallel ladder. Okay. Now this the x is the modified A. So this is A and no modification, no other circuit. X equal to A and y is the modified B. So this is the circuit of y that comes from the B. So at each input, of B input, we replace with the Y. Replace with the Y. And this is the selection pin, S0, S1 and carry in. Okay. So depending on the selection pin S0, S1 and carry in, the modified B will be applied at the input of Y. And that particular operation will get performed. So we have designed 4-bit arithmetic circuit. 4-bit arithmetic circuit that will perform different arithmetic operation. What arithmetic operation it will perform? This 8 different arithmetic operations it will perform. 8 different arithmetic operation. So what we have done till now, we have designed the arithmetic circuit and we have designed the circuit for Y that will modify input B in terms of the selection pin automatically to perform the required arithmetic operation. Clear? Next, we want to design the logic circuit. Okay, before we design the logic circuit, there is a sample example. So this is the practice problem, okay? Design an adder subtractor circuit with one selection variable S and two inputs A and B. In this case, it is only an adder subtractor circuit with one selection variable S. Okay? If there's a one selection variable, then only two different operations you can perform. What are the operations you can perform? When the selection variable S equal to 0, look at over here, selection variable S equal to 0. The circuit perform A plus B. And when the selection variable S equal to 1, the circuit perform A minus B by taking 2's complement of B. Okay, so two different operations. When S equal to 0, A plus B, and when S equal to 1, A minus B by taking 2's complement of B. So look at over here. A plus B. When carry in equal to 0, it will perform, and S equal to 0, it will perform A plus B. And when S equal to 1, it will perform A minus B by taking 2's complement. This is A plus B bar. So in this case, we need to design a circuit like before in terms of Y that will modify this B depending on the selection pin. When the selection pin is S equal to 0 and carry in equal to 0, that means when the selection pin will be 0, 0. Look at over here. When the selection pin is 0, 0, 0, okay, there can be 4-way A can be A and B. Okay, A can be 0, 0, 0, 1, 1, 0, 1, 1. Okay, so when A, B, they are all 0, 0, X equal to 0, X there is no change, X equal to A, and Y equal to modified B. When the selection pin 0, 0, there will be no modification of B. Look at over here. When the selection pin 0, 0, carry equal to 0 and S equal to 0, A and B no modification. So X equal to A, Y equal to B. Okay, X equal to A and Y equal to B. Clear? Because when the selection pin is S equal to 0, it will perform A plus B. To perform A plus B, we don't need to modify B. It is as it is and carry n equal to 0. Keep it as it is and we get A plus B operation. So X equal to A and carry n equal to S. That means when carry n equal to S, that means carry n equal to 0, S equal to 0, it is performing A plus B. Clear? When S equal to 1, S equal to, in this case, S equal to 1. S equal to 1. Okay, this S. S equal to 1. Okay. In that case, we need to invert B to B1. We don't change A. We don't change A. We change B to B1. So look at over here. This is your A and B input, but Y equal to invert of B. This Y part is the invert of B. Y part is the invert of B. So if we solve the logic equation for it, X equal to A, Y equal to B exclusive or X. Look at over here. This is the exclusive OR operation. Okay. B exclusive or X. S. B exclusive or S. When they are opposite, we get high output. When they are opposite, when B and S are opposite, we get high output. When they are equal, we get low output. So if we consider this portion, this is B, this is S, okay, and this is Y. So what is the equation of Y? B exclusive or S, okay, B exclusive or X. That's the equation of Y. Equation of X equal to this, and carry equal to S. Okay, in this case, in the first group, carry equal to 0 to get the addition operation. The second group, carry equal to 1 to perform the subtraction operation. So this is the logic equation of X, Y, and carry. So we have found the logic equation. Now we can draw the circuit. So what is the circuit? Look at over here. S. This is S. S. Okay. Carry equal to S. Okay. This is X equal to A. No change. And in place of Y, we give the modified circuit. B exclusive or S. B exclusive or S. That's the modified circuit. Okay, modified circuit. B exclusive or S. So we have designed the circuit that will modify B input depending on the selection pin to perform different arithmetic operation. So this is our 4-bit adder subtractor circuit that will perform addition operation when S equal to 0, and it will perform subtraction operation when S equal to 1. This is 4-bit. If they in the question paper they tell you to draw the for 2-bit, then 2 block will do. For 1-bit, 1 block. For 8-bit, there will be 8 block like that. Okay. Yes, at 4-bit is the standard. I think because our ALU is 4-bit ALU, we are covering in this syllabus. So it is usually 4-bit, but sometimes on the question paper they can specify. Okay, draw circuit for 2-bit, then 2 block. Draw circuit for 3-bit, then 3 block. Okay. So that's the design of 4-bit adder subtractor circuit. On our next class, we'll cover logic unit design.